All right, it is the 10th of September, 2025, approximately 8:12 a.m. Today we are going to be going over, we're going to be getting into dominant input 1.3 symmetric groups with special attention given to Kekola's solutions, which are noted in the description as usual. And we're just going to proceed exercise by exercise. So for exercise 1 in section 1.3, let sigma tau be within S5 be defined by sigma from 1 to 3, which defines these which is defined by 1 to 3, 2 to 4, 3 to 5, 4 to 2, 5 to 1. And tau defined by 1 to 5, 1 mapped to 5, so 2 mapped to 3, 3 mapped to 2, 4 mapped to itself, 5 mapped to 1, right? And so for exercise 1, find the cycle decompositions of sigma, tau, sigma squared, sigma tau, tau sigma, and tau squared sigma. So intuitively, you'd follow the orbit of each element to build disjoint cycles. For products, apply the rightmost map first. Once an element's cycle is recorded, skip it. This is, disjoint cycles commute. So let's try and look at this a bit more rigorously. So for the proof, right? Step 1, sigma and tau in cycles. So let's trace orbits, right? So what does sigma look like, right? So it maps 1 to 3, 2 to 4, 3 to 5, 4 to 2, 5 to 1. Well, so let's take a look at this, right? So 1 to 3. Okay, all of a sudden there's this 2 to 4 business going on, right? 2 to 4, 3 to 5, 5 to 1. Okay? That's sigma. Now, what about tau? Well, tau maps 1 to 5, 2 to 3. So let's 1 to 5. This 2 shows up out of nowhere, so 3 to 2. So 3 goes back to 2. 4 to 4. 4 to 4 That's kind of its own thing. We'd usually not include such a thing, right? This single element thing here. But where does 5 go? 5 goes back to 1. So this would be written open parentheses 1, 5, close parentheses 2, 3, close, open parentheses 2, 3, close parentheses. Yeah, so that's how you'd write it. You wouldn't include this part because it's in a sense a trivial thing, but you know, a lot of things could be considered trivial, but it's not that they don't matter, it's just that, well, it's just easier to write it over and over and over again if you get rid of this, but I kind of like the idea of including it just to, you know, show it exists. So that way it's like, well, somebody looks back at it, they can intuit that like, oh, okay, this is a thing. So, but such is not the case. So that's equal to tau. So we have each of these defined within cycle notation, right? This is cycle notation. Step 2. Let's look specifically at sigma squared. What does squaring them even look like, right? So we looked at that earlier, I believe, but let's look at it here again, right? So since open parentheses 1, 3, 5, close parentheses squared is equal to open parentheses 1, 5, 3, close parentheses, right? So open parentheses 1, 3, 5, close parentheses, open parentheses 1, 3, 5. One goes to 3, 3 goes to 5, 5 goes back to 3, 3 goes back to 1. So 1, 5, 3. 1 goes to 3, 3 goes to 5. And open parentheses 2, 4, close parentheses squared is equal to 1. It's probably a better way of writing out how exactly the thinking of this goes, right? So I'm trying to think of that. Probably, let me think. If I can think of a better way, trying to write it that way, because if you can find like a more intuitive way to write a thing, that's usually better for, well, pedagogically speaking, right? So I can't really think of one, but you know, this thing is 2 goes to 4, 4 goes to 2, completes itself there. It's equal to the identity. Well, is equal to 1. And from that, well, you take these two things, right? What does that get you? Get you sigma squared is equal to, open parentheses, 1, 5, 3. If there is something, if I think of something by which I can more better express that, then I'll include it. I don't think I'm going to be able to do it within an hour, 30 minutes, but who knows? So we have that sigma squared is equal to, open parentheses 1, 5, 3, close parentheses. So let's keep that in the back of our minds for now, because we're running out of void space. I like teaching on a big whiteboard. I feel like, you know, there's certainly something to be said about, you know, writing on a small whiteboard that's just right in front of you. But it's like, this is something traditional to it. Also, I feel like the pacing is a bit better because it takes me longer to write on a board, because this is a bigger space than a tinier whiteboard, right? So it's easier to follow along, at least in my own experience. But anyhow, for step 3, we want to consider sigma tau. So how this works is we apply tau, then sigma. It's the nature of the structure. So let's track 2 here. Yeah, let's track 2. What do we do that? Let's see. Checking 4. So let's track 2. Right, so 2 goes to 3 by tau. 2 goes to 3 by tau. And then 3 goes to 5. Oops. 3 goes to 5 by sigma. What does 5 go to? 5 goes to 1 by tau. One goes to 3 by sigma. 3 goes to 2 by tau. Right? And so what does this give us? This gives us a 4 cycle. 2 open parentheses, 2, 5, 1, 3, close parentheses. Right, so look here. 2 goes to 3. Bop teleports over here, right? So 5 goes to 1. 5 goes to 1, sorry. Teleports over here back. 5 goes to 1. Teleports back over here. 1 goes to 3. Teleports back over here. 3 goes to 2. Right? And then we just rotate again. So we get a 4 cycle. 2 open parentheses, 2, 5, 1, 3, close parentheses. So now let's look at 4, because we didn't cover 4 in any of this. So but this, it's like why track 2, right? Well, you can see it, like 2 goes over as many of the elements. Well, does it go, what is it? So it's like 5, 1. So it's like, how do I say this? 2 is a very convenient one to pick. And the reason it's a convenient one to pick, in this case, there's a lot more that can be said about why we chose to track 2, right? But I'm just going to leave it at that. Track a specific one, follow it, get a 4 cycle. That's what we did here. That's not like a general sort of step-by-step thing, but just mentioning what we did here to find it. So find that 4 cycle, which, by the way, is a nice clump of almost all of the numbers except for 4. So, which is part of the convenience of it. So 4 goes back to 4 by tau, right? So 4 goes back to 4. 4 goes to 2. Wait, sorry. Yeah, so 4 was, remember, 4 is an identity sort of thing over here. So by tau, it goes back to itself. Let me check this off. Well, let me get rid of this first. Four goes to 4 via tau. 4 goes to 2 via sigma, and we complete a cycle. It goes to 2. So 4 goes to itself, which goes to 2. And that 2 goes right back here. If I didn't write it incorrectly. I mean, it goes to 2 either way, right? Regardless of whether or not this thing is written up to par for what it's supposed to be. But this shows that sigma tau is equal to, open parentheses, 2, 5, 3, 4. Why get rid of the 1, right? Why get rid of the 1? So it's kind of for the same reason why you'd get rid of this case here with like this trivial instance here. It's sort of trivialized out in a way. It's like a cost-cutting sort of thing. I don't know. It's not. It's like sort of like a convention. It's convention. I wish I knew the origins of that more. I wish I could say more on that, but I'm lacking the information and the words. So, but sigma tau is then equal to the 4 cycle, open parentheses, 2, 5, 3, 4. There's a reason for it. I'm just not coming up with it. Okay. So let's go to, so keep that. Let's go to tau sigma now. After I check this. I'll come up with the convention. I'll find out why. I need to make note of that to find out why these things are. So I know, it's probably going to be something like, well, that's just how we've always done it. But it's like, well, always since when? It's like, well, that makes it mean something more, right? That's always nice. Okay, so step 4, tau sigma. Apply sigma first, then tau. So 1 goes to 3. 1 goes to 3 via, oh, goodness, why do I keep doing that? That's so silly. Okay. 1 goes to 3 via sigma. Where does 3 go via tau? 3 goes to 2 via tau. Where does 2 go? Via sigma. Well, that goes to 4. Now, where's 4 go via tau? Well, it goes back to itself, right? So it doesn't exist. No, but it does. It's just, which is why I'm like, you know, why not? Why not just include it there? It's because whenever we do a whole bunch of complicated stuff involving this later on, we don't want to have to write it over and over again. Well, it's like, too bad. No. No. But, yeah, so that goes back to 4. And continuing this, let's, so does that hit all of them? What about 5? What about 5? What happens to 5? Well, let's see. Oh. This is not equal to that. This is rather us just tracking 1. Track. It's a case-by-case thing, right? Whichever one you sort of choose depends on what you're trying to look at here. And in this case, sigma gets operated on first. 1 goes through as many of them as we can, right? And so 5 is the one that's left out, and so we'd zero in on that, and then we'd go after that after the fact. So yeah, okay. So for 5, where does 5 go via sigma? 5 goes to 1, and we're right back where we started, right? So 5 goes to 1. It's what we needed. And it's not, and it's not like the 5 is not like the 4 case, so it doesn't get its own little mention like in the previous sigma tau case. So that is something. Goes to 1. Let's move on to 5 here. Okay, so tau squared sigma. Now, yeah, so since tau is a product of 2 cycles, tau squared is equal to 1. Hence, tau squared sigma is equal to sigma, which is just equal to open parentheses 1, 3, 5, close parentheses, open parentheses 2, 4. We were asked for all the results. Let's take a look at all of them. So for sigma, we got open parentheses 1, 3, 5, close parentheses, open parentheses 2, 4. For tau, we've got open parentheses 1, 5, close parentheses, open parentheses 2, 3, close parentheses. Sigma squared is equal to open parentheses 1, 5, 3, close parentheses. For sigma tau, we've got open parentheses 2, 5, 3, 4, close parentheses. We've got for tau sigma, we have open parentheses 1, 2, 4, 3, close parentheses. And for tau squared sigma, we have open parentheses 1, 3, 5, close parentheses, open parentheses 2, 4. Thus completing that first exercise, and we can move on to the second one. So for exercise 2, let sigma and tau be within the S sub 15 symmetric group and be defined, well, let sigma and tau be elements of the symmetric symmetric group S sub 15 be defined by sigma is so we're given for sigma 1 goes to 13, 2 goes back to itself, 3 goes to 15, 4 goes to 14. We'll order these in a moment, but just writing them out. 5 goes to 10, 6 goes back to itself, 7 goes to 12, 8 goes to 3, 9 goes to 4, 10 goes to 1, 11 goes to 7, 12 goes to 9, 13 goes to 5, 14 goes to 11, and 15 goes to 8. That's for sigma. Let's try and keep some space for tau next time. But tau, for tau we have 1 goes to 14, 2 goes to 9, 3 goes to 10. Oops. Four goes to 2, 5 goes to 12, 6 goes to 6, 7 goes to 5, 8 goes to 11, 9 goes to 15, 10 goes to 3, 11 goes to 8, 12 goes to 7, 13 goes to 4, 14 goes to 1, 15 goes to 13, And we have to do what? Well, nobody's holding you at gunpoint to do these, but find the cycle decompositions. Be such a weird thing to be held at gunpoint for. But anyways, find the cycle decompositions of sigma, tau, sigma, tau, sigma squared, sigma, tau, tau, sigma, and tau squared sigma. So intuitively, you build each permutation by following orbits until they close, right? So like we did last time. For products, apply the rightmost map first. Disjoint cycles commute. So once an element cycle is recorded, you skip it, right? So that's the sort of intuition behind that. Now let's go after this with that in mind. So let's do this more rigorously with an almost completely dried up dry erase marker. No, it's still fine. It's still holding on. Okay, step one. Let's look at sigma in terms of cycles. It's pretty sigma, you know, it's pretty sigma. But let's trace. So we have one goes to 13. One goes to 13. Where does 13 go? 13 goes to 5. Where does 5 go? So 5 goes to 10. Where does 10 go? 10 goes back to 1. There we go. We're done. No. But, because there's more to do, right? So, and because we haven't hit all of these elements here, so all of these different transitions because they're disjoint. So 3, next up we have 3. Well, so, okay, I should know because the next one I listed was 2, right? And we wouldn't mention that because of, you know, it's sort of a trivial thing, but, you know, some things which are trivial will prove not so trivial if given the attention or the time to mean something. But no, everything matters to a certain degree, right? So it's like, well, 2 goes to itself. That's fixed. So I'll just have this blocked off for as a parenthetical, just in case. So 3 goes to, where does 3 go? 3 goes to 15. Where does 15 goes? 8. Where does 8 go? 8 goes back to 3. So that's closed. And what else is there? Well, there's 4. Does 4 do anything? Let's see. Okay, so 4 goes to 14. Where does 14 go? 14 goes to 11. Right, so that's good. Where does 11 go? 11 goes to 7. That's pretty nice. 7, 11. And where does 7 go? 7 goes to 12. 12 goes to 9. 9 goes right back to 4. And where did that lead you? Back to me, right? No. Okay. Now what about 6 though? We haven't really touched upon 6 here. So 6, well, that just goes back to itself, right? So that's also, 6 is fixed. That rhymes kind of. It rhymes enough for poetry, right? No. So that's sigma in cycles there. So let's look at tau. Whoops. Before that, let's write down what sigma actually is, right? So sigma is equal to 1, 13, 5, open parentheses 1, 13, 5, 10, close parentheses, open parentheses 3, 15, 8, close parentheses. Just pretend that I'm writing it over here. So open parentheses 4, 14, 11, 7, 12, 9, close parentheses. We have our sigma, and it is quite sigma. No, but let's go to tau. So stupid. Okay. So tau in cycles. Tao Te Ching and cycles. So let's trace again. Where does 1 go? 1 goes to 14. Where does 14 go? Back to 1. Done. It's a closed thing. Don't really need to think too much about that, but let's look at this next one. Where does 2 go? 2 goes to 9. 2 goes to 9. Where does 9 go? 9 goes to 15. Where does 15 go? 15 goes to 13. Where does 13 go? That goes to 4. Where does 4 go? 4 goes back to 2. There we go. Well, never saw 2. It's just back relative to our position, right? So where does 3 go? 3 goes to 10. Where does 10 go? Back to 3. This is sort of the, I don't want to say banality. I mean, because it can be fun. But it's just, these things hold and they're consistent, and that's why we like them. So, not much shock factor there, right? Nothing really too new gleaned out of it, but we'll get into some more rigorous stuff here in a 3 goes to 10 back to 3. How about 8? I mean, no. Let's see. Where does 4 go? 4 is already covered. Okay, how about 5? 5's kind of, nope, that's 15. So we haven't covered 5 yet, so let's go to 5. Five goes to 12, goes to 7, goes to 5. So 5 goes to 12, 12 goes to 7, 7 goes to 5. How about 6? Right, 6 is fixed. Like we're in a Dr. Seuss book. So 6 goes to 6, and 6 is fixed. And the cat sat on a mat and wore a nice hat. It was very fat. Kind of like me. So, that holds there, but what else? How about 8? So 8 goes to 11, which goes back to 8. Anything else? I think we've covered everything in that. Not a single stone unturned. We can just put that right. So 1, 2, 3, 4, 5, 6. Where's 7? Where is that? There it is. 7, 8, 9, 10, 11, 12, 13, 14, 15. There we go. So what does this mean for tau? Let's break this down into its disjoint cycles. So first we have 1 and 14. Open parentheses 1, 14, close parentheses. Open parentheses 2, 9, 15, 13, oh no, 4, yeah, close parentheses. Open parentheses 3, 10, close parentheses, open parentheses 5, 12, 7, 5, 12, 7, close parentheses, open parentheses 8, 11, close parentheses. Okay? So now we have sigma and tau. Now we can manipulate both of those. See about this. So it asked for sigma squared next. Step 3. So we'll do this by square each disjoint cycle of sigma. Open parentheses, 1, 13, 5, 10 squared we get one, open parentheses 1, 5, close parentheses, open parentheses, 13, 10, close parentheses. Next, open parentheses 3, 15, not my tempo, 3, 15, 8, close parentheses, squared is equal to open parentheses 3, 8, 15, maybe I should just underscore it to show. I can see how that could go wrong, but underscoring like that preserves some space. Okay. Yeah, that's better. So that's for open parentheses 3, 15, 8 squared. Now let's move on to this next one, which is a bit larger. Open parentheses 4, 14, 11, 7, 12, 9, close parentheses squared, which is equal to so that's a good, so I just sort of thought like, okay, how can I show this to be the case? Well, basically what's going on here with these square things is, so, no, you don't know because I meant, well, maybe you do. So say that this is equal to x, right? So you're multiplying it by itself, and you do the same thing that we did for sigma and tau, you do to this. It's just that this is, so you'd say, so let's say x sub whatever, and within the integers, that belongs to both big X sub 1 and big X sub 2. It's a weird way of putting it because those are two sets, but these things are equal, so anyway, you go X sub n, you'd address the big X sub 2 first, and then you get to some other X sub n, and then you go X sub 1, big X sub 1, and then you get to some other X sub n. That's what's going on here whenever you square it. So, I mean, there's also like general tricks and stuff like that, like you saw with anything that has like these two and then you square it, that will get you the identity, right? So, and you can break those things down, that's an interesting case, right? So it's like, well, xy, xy, x goes to y via 1, y goes back to x via 2, x goes to y, you know, on and on and on. So you can see how that maps out, and there's a whole bunch of little tricks that you can do there where you can get interesting things. So that's the sort of underlying thing that's what's going on under the hood. So yeah, that would take forever. But it's not exactly not par for the course for what we're doing, but I might have to do that. I might have to do that. The next time I go around, I might have to do that. So for now, though, let's just stick to saying, you know, let's just stick for having this be under the hood. I don't like doing that, but we're limited. Four, 14, 11, 7, 12, 9, all of this squared. What does that get you? Gets you, open parentheses, 4, 11, 12, close parentheses. Open parentheses, 7, 9, 14, close parentheses. And that is all of our disjoint cycles, right? So what can we say about sigma? Well, sigma squared, I mean to say, is equal to wrote it differently here, but I'll explain why. It's equal to open parentheses 1, 5, close parentheses, open parentheses 2, 8, 15, close parentheses, open parentheses 4, 11, 12, close parentheses, open parentheses 7, 9, 14, close parentheses, open parentheses 10, 13. It's a general rule. If you can't write an underscore in between two numbers, they're probably too close. So here we go. If you put them too high and they look like minus signs, they're probably too high. So why move this? Why move this at the end, right? Okay, so let's think about this. 1, 13, 5, 10. Well, it's just sort of an indexing thing, really. It's an indexing thing in a way. So 1, 5, 3, 4, 7, 10. That's it. That's literally there's I'm sure you could sort of like rigor that up as to like why that would be there, but that's like sort of the naming convention why 10's there. So, but without further ado, let's just move on to sigma tau. I have to pick up the pace. I've been talking too much. Outside of the context. So step 4. Sigma tau. Phi tau before sigma track 1 So 1 goes to 14 via tau. Where does 14 go? Via sigma. 14 goes to 11 via sigma. Where does 11 go via tau? 11 goes to 8. Okay, how about 8 via sigma? 3. Okay, how about 3 via tau? 10. Good. Now, how about this? 10 via sigma? That goes back to 1. This gives us, open parentheses 1, 11, 3. Okay. let's track 2. Where does 2 go via tau? 2 goes to 9. 9 goes to 4 via sigma. Where does 4 go? Via tau. 4 goes to 2. Where does 2 go? Via sigma. Let's go anywhere. Oh. It's supposed to be a 1 up there. So we've got open parentheses 2, 4, close parentheses. So we haven't really dealt with 5 yet. Five goes to 12, goes to 9, goes to 15, which goes to 8, which goes to 11, which goes to 7, which goes to 5. Okay. Got 1, 2, 3. 1, 2, 3, 4, 5. How about 6? Well, 6 is fixed. 7 is accounted for. How about 8? 8, 9, 9, 10. How about 10? This is taking a bit more time than I expected. So via tau, where does 10 go? 10 goes to 3. Oops. Where does 3 go via sigma? 3 goes to 15. Where does 15 go via tau? Wait a second. Let me see. 13, where does 13 go via sigma? Five. Where does 5 go via tau? And where does 12 go via where does 12 go via oopsies 15 to what was I saying? Yeah, 15 to that. 12 goes to what via sigma? 12 goes to 9. No? Yeah. Yeah. 12 goes to 9. And that's actually just part of the cycle there. So, what does this mean? This means we also have 5, 9, 8, 7, 10. So we have open parentheses 5, 9, 8, 7, 10, 15. Close parentheses. Okay. Now, how about the 13, 14? Well, okay, so yeah, that should be noted. Thirteen goes to 4, 4 goes to 14, 14 goes to itself, so yeah, 13 goes to 14, 14 eventually goes back to 13 under sigma tau. So what we end up having here is this little menagerie, disjoint cycles, and with which we can say, okay, sigma tau is equal to open parentheses 1, 11, 3, close parentheses, open parentheses 2, 4, close parentheses, open parentheses, 5, 9, 8, 7, 10, 15, close parentheses, open parentheses, 13, 14, close parentheses. That's what we have for sigma tau. Now we'll pick up where we left off in the next one.